Assalamualaikum and hi to everyone. Thank you for watching this video. So in this video, we'll continue on another part of chapter 9, visual memory. So in the previous video, we already learned about the background, the demand paging and the page fault regarding the visual memory. So next, for this part, we will continue on the page replacement, allocation of frame, thrashing and operating system example. So first we go for the page replacement. Okay. This part to prevent the over allocation of the memory by modifying the page fault service routine to include the page replacement. So in order to prevent the over allocation, we need to use the page replacement. So we use the modify bin to reduce the overhead of page transfers and only modify the pages are written to this. Means that we only the modified pages will be written to the disk. So page replacement completes the separation between the logical memory and the physical memory. Large visual memory can be provided on a smaller physical memory. So it means, let's say our memory is only 8 gigabyte. That is the physical that we already have. We can use a large visual memory on the small physical memory. So the need for the page replacement, okay, you can look at this diagram. PC1 here, this is the PC or desktop or laptop. We have the logical memory for user 1 because in OS we have several type of users. So user 1, so we have here H and load M here, J and M. So PC1 at here. Here is the page table, frame 3, 4, 5. So this one is the valid and invalid bit, V for valid and I for invalid. Okay, this one is referred to the physical memory, the physical memory that available at the device. Okay, we have 0 until 7 here. So D, H, load M here refer to this part 1. So frame 0, frame 1. So frame here 0, 1, 1 refer to frame 4. So frame 4 is valid, then goes to the physical memory address 4. Here we have A, B, D and E. So logical memory for user number 2. Okay, and then we have the frame bit, valid, invalid, valid, valid. Okay, so 6 here refer to this one, 6, the address number 6. So 6 here at 0. So the first 0 here is A. So A and A here. So this is the basically when we how to read the memory, logical memory, and then page table with the physical memory, and then it will swap in and swap out from this physical memory to the secondary disk. So for the basic page replacement, number 1, we need to find the location on the desired page on the disk. Number 2, find a free frame. If there is a free frame, then we can use it. If there is no free frame available, so use a page replacement algorithm to select the victim frame. Okay, the term is quite victim, the victim frame, in order to replace the page. So write the victim frame to the disk if dirty. So what is dirty? Dirty means modify bits. Okay, if we modify bit, then we write to the disk. Okay, and then number 3, bring the desired page into the newly free frame and update the page and frame table. So basically we have this part. Later on we need to update this table. So this one we have the victim. Okay, later on we look more on the demonstration. Number 4, continue the process by restarting the instruction that caused the threat. And then you should remember about the 2-page transfer for page fault will increasing the EAT. So page replacement process, here we have the page table. Okay, you can ignore this pencil. Okay, we have the page table, the same part, we still have the physical memory, and we have the disk here. So frame refer to this column, valid and invalid refer to this column. Okay, based on the step number 1, okay, this one is the victim, the one that we want to use. So swap out the victim page and then swap the desired page into this location. Okay, so number 1, first you swap the victim page. Number 2, change to the invalid before this is valid. So you change to the valid. And then swap the desired page in and reset back the page table. Okay, the next part is about the page and frame replacement algorithm. Again, we have another algorithm. So frame allocation algorithm determines how many frames to give each process and which frame to be replaced. That is the frame allocation algorithm. The next algorithm is page replacement algorithm. So in the page replacement algorithm, we want to lower the page fault. We want to decrease or try to minimize the page fault rate on both first access and the reaccess. And then evaluate the algorithm by running it on a particular string of the memory references and computing the number of page fault on that string. So string is just page numbers, not the full address. Okay, the full address is another part. And then repeating the access to the same page does not cause a page fault. And result depends on the number of frames that available during that time. And in all our example, the referencing of reference page number is 7012030303021201701701. So this one is the page reference number. Okay, next you can look at the graph of the PF versus numbers of frame. PF refer to page fault. So this one is the number of frame in the table, and then we have the number of page fault. So number of frame 1, so higher page fault here. It means when the numbers of frame increase, so the number of page fault can be decreased. This is what we can conclude from this graph. Okay, so the next is the algorithm first in, first out. Okay, the FIFO algorithm. So the reference string here is we have 7, 0, 1, 2, 0, 3, 0, 4, 2, 3, 0, 3, 0, 3, 2, 1, 2, 0, 1, 7, 0, 1. So this is the reference string. And then we have 3 frames. So 3 pages can be in a memory at a time per process. So we have this reference string. So we have the page frames. So based on this part, we have 15 page fault. It can vary by reference string. Consider 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5. So adding more frame can cause more page faults. This one under the BELADY'S anomaly. Okay. Yeah, how to track the ages of pages? Just use the FIFO queue. Okay, on the FIFO illustrating Belady's anomaly, okay, what can you conclude from this graph? Okay, we have the numbers of frame here and the numbers of pages fold here. When page frame is 1, so page fold is 12. Number of frame is 2, number of here 12. And then 3, it decrease, and then 4, it increase back, and then when it decrease, okay, when we increase the number, it decrease, and then it's static. So this one is from before illustrating by Belady's anomaly. Okay, for the second part is Belady's optimal. Okay, later on we go through the algorithms. Okay, this one is used for future knowledge. Okay, in Belady's optimal, it used the future knowledge. In FIFO, it's just use the first in, first out. Okay, first in, so first out. Okay, this one is another part. For the Belady's optimal, it use the future knowledge. So replace the page will not be used for longest period of time, and 9 is the optimal for the example. Okay, how do you know this? Okay, I can't read the feature. We cannot read the feature, but how we want to use this feature knowledge? And then use for measuring how well your algorithm performs. So, okay, later on we go for the tutorial. Number 3, least recently used LRU. So basically at this part you should know the type of algorithm, and least recently used use past knowledge. Belady's optimal, Belady's anomaly, we use the future. This one we use the past knowledge. So replace the page that has not been used in the most amount of time, and then associate the time of last use with each page. So we still use the same reference string here. So 12-fold better than the FIFO, but worse than the optimal. Okay, we have FIFO, Belady's optimal, and LRU. So generally, good algorithm and frequently used is this algorithm, least recently used. Okay, in LRU, it will counter the implementation. Okay. Every page entry has a counter, and every time page is referenced through this entry, copy the clock into the counter. When a page needs to be changed, look at the counters to find the smallest value and then search through the table needed. So we look at the counter, find the smallest value, and then we search through the table. Okay, first is about the counter implementation. Second, stack implementation. So keep a stack of page numbers in a double link form. Page reference, move it to the top. Okay, and require 6 pointer to be changed. But each update more expensive. So no search for the replacement. LRU and optimal are cases of stack algorithm that don't have the Belady's anomaly. This one use stack to record most recent page references. Okay, so basically we have P4, we have the optimal, and then we have the LRU. So this one is LRU approximation. About the demonstration on how the algorithm works, later on I will create another video. So LRU needs a special hardware and still slow. Okay, use the reference bit with each page associated with a bit. So initially the bit is 0, and when page is referenced, bit set to 1. So from 0 it will set to the 1. Replace any with the reference bit 0 if 1 exists. So we do not know the order in this LRU algorithm. Second chance algorithm, generally FIFO, we use the FIFO plus the hardware provided reference bit. And then we use the clock replacement if the page to be replaced has this reference bit 0, so replace it. If the reference bit 1, then set the reference bit 0 and leave page in the memory. Replace the next page subject to the same rules. Okay, for counting algorithm, keep a counter of the number of references that have been made each page, which is not common, and LFU, least frequently used algorithm, replace the page with the smallest count. MFU, most frequently used algorithm, based on the agreement that the page with the smallest count was probably just brought in and has yet to be used. All of these algorithms have OS guessing about the future pages access. And some applications have better knowledge, example in terms of the databases. Memory incentive application can cause double bufferings to your process, and OS keeps copy on the page in the memory as input and output buffer. Application keeps pages in memory for its own work, and then operating system can given direct access to the disk, getting out the way of the application. So this one is raw disk mode. Okay, the mode is raw disk, and bypass buffering, locking, and extra. Okay, next is about the allocation of the frames. So each process need minimum number of frames. Example here, let's say IBM 370, 6 pages to handle SS move instruction. So every process has the number of frame. So instruction is 6 byte size of the frame. Might span 2 pages. So 2 pages to handle from and 2 pages to handle to. So maximum of course is total frames in the system. And 2 major allocation schemes, fixed allocation and priority allocation. So we have many variation varies. Okay, this one is allocation of frame, and then we have a fixed allocation. So equal allocation, for example, if there are 10 frames, after allocating frame for the OS and 5 processes, give each process 20 frames. Mean we have the fixed 100 frame, we have 5 process, so 100 divided by 5, then you get 20 frame. So keep some of as a free frame buffer pool. Professional proportional allocation. So allocate according to the size of the process. So means it depends on the process size. Dynamic as a degree of multiprogramming, process size change. So size of process, we have P1, okay, S here, the cumulative here, and then M, total number of the frames. E is allocation for process size, and then the total of size, and then time with the total number of frame. So let's say the M, total number of frame is 64. We have size of process 1, 10, size of process 2, 1 to 7. So the allocation for this process, okay, 10 divide by the total number 137, total number of this part, total number of S, okay, 137 times with the 64. Okay, time of the 62. Okay, here is 62, and then for the allocation for the process 2, do the same things. Then you will get the answer will be 4 and 57. Is it correct? Okay, never mind. I will double check on that part. Okay. Okay, time 64. Okay, here is M, so M64 here. And then priority allocation, use the proportional allocation schemes using the priorities rather than the size. So this one is referred to the priorities. So if process P I generate a page fault, select the replacement one of its frame, and then select for the replacement of frame from a process with lower priority number. Okay, this one is global versus local allocation. So for the global replacement, process select a replacement frame from the set of all frames, and one process can take a frame from another, but then the process execution time can vary greatly, but greater throughput, so more common. For local replacement, each process select from only its own set of allocated frame, and more consistent per process performance, but possibly underutilize the memory. Okay, next we have the NUMA, non-uniform memory access. Okay, so far, in all memory access are accessed equally. Many systems are NUMA, which is non-uniform memory access. To speed of access to the memory varies. So speed, the process, the time taken in order to access to the memory varies. So consider a system board containing CPUs and the memory, so interconnected over a system bus. So this part is based on the NUMA part. And optical performance come from allocating memory close to the CPU on which the thread is scheduled, and modifying the scheduler to schedule the thread on the same system board when possible. So Solaris, another CPU, solved by creating the I group. So structure to the CPU memory low latency groups, and then use my schedule and pager. When possible, schedule all the thread of the process and allocate all the memory for the process within the I group. So this part is solved by the Solaris. Okay, the next part is about the thrashing. So if a process does not have enough pages, the page fall rate is high. So page fall is to get page. Replace the existing frame, but quickly did replace a frame back. So these lead to the low CPU utilization. Operating system thinking that it needs to increase the degree of multiprogramming, and another process added to the system. Thrashing is equal to a process is busy swapping pages in and out. Okay. So you can refer to this graph, degree of multiprogramming and CPU utilization. So at this point, we call as the thrashing. Swapping in and out. Okay, the next point, we should the question about the why does the thrashing occurs? Okay, because of the cumulative size of the locality is bigger than the total memory size. So this is the reason why the thrashing occur in the process in the memory. The limit effect by using local or parity page replacement. Okay, the frequency of page fall, more direct approach than the WSS, and establish acceptable page fall frequency PFF, and use local replacement policy. So if actual read too low, process loss frame. If actual rate too high, process gain frame. So this is the relationship between the number of frames and the page fall rate. Can refer to the graph. It's decrease when the number of frame increase. Okay, this one is similar like the previous graph that I showed you. Okay. Next is about the memory map file. So memory map file, the input output, allow the file input output to be treated as a routine memory access by mapping a disk block to a page memory. A file is initially read using the demand paging. A page size portion of the file is read from the file system into a physical page. Subsequent reads or writes to the from and the file are treated as ordinary memory accesses. Okay, and then simplify the speed of file access by driving file input and output through the memory rather than read and write function system call. And then it also allows several processes to map the same file and allowing the pages in memory to be shared to the others. But when does the written data make it to the disk? Okay, periodically and or add a file close function time. So use this function. Okay, example here, when the pages scans for the dirty pages. So it will return data to the disk. So this one is the memory map file processed in a virtual memory. Okay, it will map to the physical memory using the patch table, and then it will write to the disk file. Okay, and then this another process. So process A and process B at the visual memory, and then it will map to the physical memory, and it will write to the disk file. Okay, this one is shared memory via the memory map input and output. So we have process 1, we have process 2, we have the shared memory file. So memory map the file, shared memory to the here, shared memory to the here. So it will map the file. Okay, other consideration need to be considered is about the pre-paging. Okay, what is the pre-paging? Pre-paging is used to reduce the large number of page fall that occurs at the process setup. And pre-page all some of the pages a process will need before they are referenced. But if the pre-page pages are unused, input, output, and memory was wasted. Okay, we can assume that as pages are pre-paged and A of a page is used. So the cost of S time A and then save page fall bigger or lesser than the cost of pre-paging as a time with 1 minus A. Unnecessary pages and A needs 0, so pre-paging losses. The other issues is about the page size. Sometimes OS designer have a choice, especially if running on the custom built CPU. The page size selection must take into consideration what are the what are the things that need to be considered is about the fragmentation, page table size, the resolution, the input output overhead, number of page fall, locality, TLB size, and effectiveness. And always power of 2 usually is the range 2 power of 12 to 2 power of 22. Okay, this one is the range of power and on average growing over time. Okay, TLB range, the amount of memory accessible from the TLB range equal to TLB size times page size. So ideally, the working set of each process is stored in the TLB. Otherwise, there is a high degree of page fall. Increase the page size may lead to an increase in fragmentation, as not all applications require a large page size. And provide multiple page size. Okay, this allow the application that provide larger page size the opportunity to use them without an increase in the fragmentation. Okay, another issue is about the program structure. Okay, this is the code. Let's say we have initial integer 1 to 8, 1 to 8 data. So each row is stored in one page. Program 1 for j equal to 0, j lesser than 1 to 8, j plus plus for the looping part. And then for I equal to 0, I is lesser than 1 to 8, I plus plus. So data I, j equal to 0. So example here, we have 16,340 page for program 1. For program 2, based on this code, we can have the 128 page all. Okay, this one is depends on the program structure. Okay, another issue is about the input and output interlock. The interlock pages must sometimes be logged into memory. Consider input and output pages that are used for copying a file from a device must be logged from being selected for eviction by a page replacement algorithm. And pinning of the pages logged into the memory. So that's for the issues regarding the visual memory. Okay, these are the several issues that need to be considered. The next part is about the OS example. So we have Windows and Solaris. For Windows, it uses demand paging with the clustering. So clustering bring in the pages surrounding to the faulting page. Process are assigned working set minimum and working set maximum. So working set minimum is the minimum number of pages the process is guaranteed to have in memory. A process may be assigned as many pages up to its working set maximum. Okay, when the amount of free memory in the system falls below a threshold, automatic working set trimming is performed to restore the amount of free memory. Working set trimming removes pages from the processes that have pages in excess of their working set minimum. Next is Solaris. So in the Solaris, maintain a list of free pages to assign faulting processes. Lots free, threshold parameters, amount of free memory to begin paging. And then we have this free, the threshold parameter to increasing the paging. And then we have the mean free, threshold parameter to being swapping. Paging is performed by page out process. And then page out scan pages using modified clock algorithm. Scan rate is the rate which pages are scanned, and this range from slow scan to the fast scan. And then page out is called more frequently depending upon amount of the free memory available. And priority paging give the priority to process code pages. So that's all for chapter 9. Okay, we already look on the algorithm, the FIFO, the LRU, the optimal, and then things that need to be considered about the page fall, and then example of the operating system which refer to the Windows and Solaris on the page fall and so on. So the next video is about the demonstration on how the process of algorithm work. So that's all. Thank you and Assalamualaikum.